Hi there, Sherwood. I did get a request today to look at one of the homework problems from section 3.4 about rates of change. And this was problem 4 in the textbook, in which we're asked to look at a square which has been inscribed in a circle. And we're supposed to figure out how fast the area is changing relative to the radius at the exact moment when the radius is 8. In other words, what's the instantaneous rate of change of the area with respect to the radius? Now, to help you understand what this problem is asking, what I've done here is to measure the radius of the circle, and you can see that as I make it larger, this number changes, getting bigger or smaller. I've also measured the area of the square, and you can watch this quantity change as the size of the square changes. Okay, so that's just to help you get your head around what's going on. And we want to know when r is 8 specifically, it's like right at that moment, right there, how fast is this number going up in relation to this number? Or to put it differently, if we were to increase r by a millionth of a centimeter, how much would you expect the area to change? Let's do calculus and find out. Here goes. Okay, so where to begin with this? Well, we'd like to get an expression that helps us understand the relationship between the radius of the circle and the area of the square. So in order to do that, let's just start from the beginning. If I can describe the side length of the square, then I can certainly write down a formula for its area. The side length squared is the area of the square. So now the question becomes, what's the relationship between these two variables? And we're going to have to be a little bit clever about this. So if I draw in this triangle, you might believe that this is a right triangle, which is also isosceles. And you can think about the properties of a square to convince yourself that that is indeed a right angle right there. So we'll go with that. And if it's a right triangle, then we can use Pythagoras on the triangle and figure out what S is in terms of R. Here goes. So Pythagoras would say this quantity squared plus this quantity squared equals this quantity squared. And so we're here. R squared plus R squared is equal to S squared. And we can combine terms. We have 2 copies of R squared. And I notice right there, as I think about it, this right here actually is the area of the square. And there's a formula for the area of the square in terms of the radius r. So maybe this is the function that we should work with. The area of the square as a function of the variable r. All right, so let me summarize that. I'm just going to erase and summarize. AR is 2r squared, is what the math is telling us. Okay. Now, in order to get a rate of change, I'll calculate a derivative. So a prime of r is the rate of change of the area with respect to the radius. And we use our derivative rules to write the derivative of r squared is 2r, and we'll multiply it by the constant 2, which gives 4r. I'll just clean that up and write 4r. And this is a formula that tells us the rate at which the area is changing. We would like to evaluate that formula at the precise moment, according to this, that the radius is 8. In other words, the formula is saying if you have a really big radius, then the rate of the change of the area is kind of big. If you have a small radius, then the area is changing at a smaller rate. Okay, so we'll go ahead and evaluate when r equals 8. This formula is telling us the rate at which the area changing is 32. And now it's a question of getting the units right. Okay, so we're thinking about the ratio of 2 quantities. The first one being area, which is measured in square inches. And the second one, the radius, is measured in inches. Okay, or this could be centimeters or something else, but square units per unit. So the conclusion here is this. At the moment that r equals 8, the area is changing at a rate of 32 square units per unit. I hope that helps, and thanks for watching.